So why is in general so hard to get samples from distributions? We need to keep in mind that always the good samples are the ones that are coming from the most likely areas in the distribution, right? And unfortunately, it's very hard to know what those areas are before fully exploring the domain. And on top of that, in general, in practice, we never have access to the normalized target distribution, meaning, in other words, that we don't know the normalizing constant z. So in practice, the only way to know the normalizing constant is by computing it, so traveling the complete domain. So for example, imagine we have this distribution. This one is unnormalized. This is the equation. So how can we get samples from here? For example, what if we want some samples from the most likely areas? It is hard to do it without actually traveling the complete domain of the distribution. So one idea could be to discretize. So if we discretize, we have some sort of grid, and then we start traveling the complete domain and calculating the probability of at each point by dividing the probability of the height in one specific point by the normalizing constant. So this thing obviously will not scale because, as you can imagine, to compute this, we will need to travel the complete domain, but as we start adding more and more dimensions, the number of states here in the grid is going to grow exponentially. So that's unfeasible in higher dimensions, right? So here's another example where we have one distribution which is like concentrated in one spike, like this one. Recall that in general, one application of distributions in the Bayesian settings is to compute expectations that rely on that distribution. For example, imagine we have this function here, and we want to compute the expectation of this function under this distribution. We know that to compute expectation, in general, we need samples from the distribution. Imagine that this distribution is the posterior, right? So we will need samples from this distribution to compute the integral. So after having the samples, then the expectation is going to be just the average of the function over those samples. So as you can imagine, this expectation is going to mostly depend on this area, because in any other area, this probability is mostly zero. So whenever we multiply the function times the probability, that term is going to be zero everywhere except here. So at the end, the only samples that will really affect my calculation are going to be the ones that fall in this area. So this explains why it is very important that we are capable of generating samples in areas where the probability mass is concentrated. So one quick note, just to align on the notation we're going to be using for normalized or unnormalized distribution. In practice, as you know, in general, we can only evaluate unnormalized distribution, meaning that to compute the normalizing term z is very expensive because we need to go over the complete domain, and that's not feasible in real case scenarios. So we will use the notation p star to refer to the unnormalized version of p. So p is going to be p star divided by the normalizing constant that we cannot compute in general in practice. So you don't get confused with the notations. And some of the wording that we are going to use is whenever we say we can evaluate p at least to within a multiplicative constant, in other words, we will be saying that we can only evaluate p star. So let's see another example that I like a lot from this book down here. I strongly recommend you to read this book. Imagine we have a plumb line, we're in a boat, and we want to calculate the average plankton concentration in a lake. So with the plumb line, we can measure the depth of the lake at any point. Of course, we can move with the boat. Okay, so let's set up the problem a little bit here. So P star is going to be the depth of the lake at any position x. Imagine that x has two dimensions, x and y, right, to locate ourselves in the lake. And imagine that the concentration is going to be a function that is, of course, depending on the position. So at the end, the average concentration of plankton is going to be this integral. We need to normalize, and we need to multiply everywhere, hopefully, the plankton concentration times the depth of the lake. So why the lake is the distribution? Because, of course, in areas where the lake is way more deep, we have more mass. So in that area, the concentration of plankton is going to matter the most compared to the areas where the depth is not so big, right? The volume of the lake is going to be our normalizing constant. So we cannot have the normalized version of P star unless we go and calculate the complete volume of the lake, so we can divide the depth on every point, right? So as you might imagine, in practice, we know nothing about the depth of the lake in every single position. We will need to measure it. And in practice, lakes are not so uniform, and we will have some underwater canyons concentrating most of the water. So the idea is to somehow discover those canyons to get the samples from, right? So imagine we have something like this. We have no idea what's going on below the water, and then we will need to travel and get the samples, and hopefully we get samples from these deep canyons. So it's going to be hard to hit those canyons without actually spending a lot of time exploring the lake. The main message here is that in general, whenever we need to make calculations that depend on one distribution of something, in real life, that distribution is going to be tough. And finding the areas where the mass is concentrated is unfeasible. And the only way to guarantee that is by traveling the whole space. The first idea to overcome this is to somehow use some sort of machine that generates any samples. And then we transform those samples. Because actually having a machine that generates samples is already non-trivial. We saw a couple of videos ago that we can generate samples with some specific methods, right? So the idea it'll be to have that machine, then generate any sample, and then with another machine to transform that sample. So after a while, we can have this situation. With the initial machine, we generate samples that are not coming from the distribution we want, but later we transform them into samples that somehow look like they are coming from our target distribution. And of course, the first idea is to use as that first machine our uniform distribution. So imagine that we use the uniform sampling method to create samples, and then using P star, which is the only thing we have in practice, we can transform those samples somehow. So recall this equation, right? We want to compute the expected value of a function under some distribution by approximating it of averaging just the samples coming from that distribution applied to f. But now our samples will come from the uniform distribution. Means that we cannot just evaluate the sample under f, we will need to transform the samples. And the proposal here is to just evaluate the sample under P star and somehow normalize the sample. With this term, we will be weighting the sample. So if the sample is more likely under P star, then this weight is going to be higher than cases where this sample coming from the uniform is low likely under P star. Then that sample is not going to weight so much in this calculation. This normalizing term here, it'll be just the sum for all our samples of P star of the sample. You can see this as a sort of like an estimation of the volume of the lake or the normalizing constant of a distribution. It'll be just going and passing over every single sample we generated, but evaluating each sample under our unnormalized target distribution. So as I said before, we can imagine this term as our transformation weight. As you can see here, this calculation is going to heavily rely in every single case where f and P star together are high, because those cases are going to be the ones that govern the final calculation. So for this method to work, we need to make sure that our uniform distribution is going to hit those areas. It's going to generate samples in where f and P star are jointly high. And that is going to happen only whenever f and p are both smooth. And that's a big assumption and restriction, of course. So if those functions are smooth, the chances of actually getting good samples from the uniform are more likely. But if we are in a situation where f or p are not smooth and they have these small deep spikes somewhere, then it's hard to get those samples from the uniform distribution unless we spend a lot of time generating different samples with the uniform. This case will work only when we have this situation, when we have a very smooth lake, and if we just use a uniform distribution, it is likely that the uniform is going to hit areas of big mass. Unfortunately, this method also is not going to work in high dimensions, because whenever we face a high dimension problem, what tends to happen is like big masses are going to be concentrated in a few areas. In other words, it's hard to be smooth in high dimensions.